Dear students, in this session we will discuss about selective assembly of mechanical parts. So before we discuss on the selective assembly of mechanical parts, we will see the difference between interchangeable assembly and selective assembly. I have taken an example of a ball bearing assembly for discussing the difference between interchangeable assembly and selective assembly. This ball bearing assembly consists of three parts: an outer ring or outer race, that is shown here, outer race, then inner race, okay. So this is shown here, inner race, and the balls, okay. Depending upon the need, we have to decide the number of balls. So these three parts are assembled together to form a ball bearing assembly. When this ball bearing assembly is manufactured with complete interchangeable parts, then we have to manufacture outer races in required number, inner races in required number, balls in required number. Then we have to assemble all the three to get the required ball bearing assembly. Suppose we want to make 1000 number of ball bearing assembly, then we have to produce 1000 number of outer races or outer ring, another 1000 number of inner races or inner ring, then another 7000 number of balls to get 1000 number of ball bearing assemblies. So when we use the concept of complete interchangeability, then after manufacturing 1000 number of outer races, 1000 number of inner races, 7000 number of balls, we can randomly pick up any one outer race from the available number of components. Similarly, we can randomly pick up any one inner race. Similarly, we can randomly pick up any 7 balls. Then we can able to assemble all the three to get the first ball bearing assembly. Similarly, we can do it for the second assembly. So we can randomly pick up an outer race, inner race, then 7 balls, assemble them to get the second sample of ball bearing assembly. So this is the concept of interchangeable assembly. Under interchangeable assembly, the parts are randomly picked from the available quantity of parts. So you can randomly pick up the 3 parts, then you can assemble them to get the required assembly. So this is the concept of interchangeable assembly. When you want to manufacture a precision component like a ball bearing using interchangeable parts is very costly. It is better to use selective assembly of the parts to manufacture the ball bearing assembly to reduce the cost. So what is selective assembly? It is shown in this figure. First, for making the first assembly, you take any one outer race, then you take any one inner race. Then before choosing the ball, you measure the gap prevailing between the outer race and inner race where you have to fix the balls. So according to the gap available, you choose the ball size from the available number of different group of balls. So here I have shown, okay, some 6 batches of different size of balls. So upon getting the first sample, inner race and outer race, then measure the gap. According to the prevailing gap, choose the size of the ball. So this is called selective assembly. Under selective assembly, any one of the parts are selectively chosen to get the required accuracy. Under interchangeable assembly, all the parts of the assembly are randomly chosen to assemble the parts. So this is the difference between interchangeable assembly and selective assembly. So where you can use selective assembly, wherever you want to maintain very close clearance, okay, where you want to manufacture components with a very close accuracy, very high accuracy, using interchangeable parts will result in higher cost. So that for the purpose of reducing the cost, we are making all the parts out of interchangeable assembly except the one of the part. So the last part to be assembled is selectively chosen upon measuring the gap prevailing in the assembly. So this is the concept of selective assembly. There are three types of selective assembly. In this session, we will discuss the first type of selective assembly with an example. So the example is shown, written on the top of the page. We need to maintain a clearance of 0.126 plus or minus 0.2 in an assembly of holes and shafts. The holes and shafts are finished in lathe with a tolerance of dia 100 H8 E8. Use the principles of selective assembly to achieve the required clearance. Find the group tolerance and group limits for holes and shafts. If you see the tolerance zone for the shaft and hole, the holes and shafts are finished to dia 100 H8 E8. So for now it is a clearance fit. Holes is having a tolerance of 100 H8. So if you see the tolerance value plus 000 plus 0.054. The shafts are manufactured with a tolerance of 100 E8. The upper limit is minus 0.072. The lower limit is minus 0.126. So the size of the shaft is to be between 99.874 99.928 according to the 100 E8 tolerance. Now the tolerance zone is shaded here. This is the tolerance zone for the hole. This is the tolerance zone for the shaft. If you want to manufacture 1000 number of assemblies of hole and shaft, you separately manufacture 1000 number of hole, then you separately manufacture 1000 number of shaft, then you can assemble each one with each one of the shaft to get the required clearance of 0.126 plus or minus 0.2. Here the holes are manufactured to 100 H8 tolerance. The shafts are manufactured to 100 E8 tolerance. The H8 and E8, the IT grade is 8 for both the shafts and hole. So this IT grade 8 can be easily achieved using a lathe. So lathe is a cheaper process to manufacture hole and shaft. So I want to manufacture the hole and shaft with the available machine without increasing the cost, but at the same time I want to attain a very close clearance of 0.126 plus or minus 0.2. Unless I adopt the selective assembly, I cannot attain the required clearance of 0.126 plus or minus 0.2 without increasing the cost of the assembly. So I don't want to increase the cost of the assembly by adopting to very accurate managing method like grinding or lapping. Still I want to produce all the holes and all the shafts using lathe itself, but I want to get a very closer clearance between the hole and shaft. So here the solution is using the principles of selective assembly, we can able to attain a closer clearance without increasing the cost of the assembly. Let us discuss about the notations to be used for solving this problem. T gauge is the tolerance of the hole, TS is the tolerance of the shaft, G gauge is the group tolerance of the hole, GS group tolerance of the shaft. Now we want to maintain a clearance of 0.126 plus or minus 0.02 between the assembly of holes and shafts. So this is taken as C is equal to C bar plus or minus K. So C bar value is 0.126 and K value is 0.02. For the purpose of achieving the required clearance, I am grouping the hole and shaft. Now this is the hole tolerance 100.000, 100.054. So this tolerance zone of hole is written here separately. Similarly, this tolerance zone of the shaft is shown here enlarged. It is shown enlarged. Now these holes are to be manufactured with a lower limit of 100, upper limit of 100.054. Similarly, the shafts are to be manufactured with a lower limit of 99.874, upper limit of 99.928. Suppose if you want to manufacture 1000 number of assemblies, then holes are separately manufactured, shafts are separately manufactured. All the holes, the size of all the holes should lie between these two limits. The size of all the 1000 shafts should lie between these two limits. Then we are going to make the assembly of these two. Now the hole is having a lower limit of 100.000, 100.054. The shaft is having a lower limit of 99.874, upper limit of 99.928. So this is the lower limit of the shaft, upper limit of the shaft. After manufacturing all the 1000 number of holes, I am going to measure each and every hole. Then I am going to group the hole into 2 or 3 depending upon its size. Suppose the size is 100.01. Okay, let us say it is coming under group 1. Suppose this size is 100.05. Let us say it is coming under group 3. So like that, after manufacturing all the 1000 number of holes, I am going to group the 1000 holes into 3 or 4 depending upon the requirement. Similarly, after manufacturing 1000 number of shafts between the two limits, okay, what are the two limits? So 99.874, 99.928. Then I am going to group the 1000 number of shaft into 3. Okay, in this example, it is shown as 3 groups A, B, C. After grouping the holes and shafts, I am going to assemble taking any one hole from the first group, assembling with any one shaft from the group A. Similarly, taking any one hole from the second group, assembling with any one shaft from the group B. So if I do like this, pairing the corresponding groups of hole and shaft, I can able to get the required clearance of 0.126 plus or minus 0.2 without increasing the cost. Here, why I am not increasing the cost is, still I am using the cheaper method of manufacturing the holes and shaft using turning, because IT grade 8 is very much achievable in turning process. So I am manufacturing all the holes in turning process. Similarly, I am manufacturing all the shafts in turning process, but by way of grouping the holes and shafts, I am able to get a very closer clearance of 0.126 plus or minus 0.2, which is otherwise not possible to achieve. If we adopt interchangeable assembly, this close clearance is not able to be achieved. So by using the selective assembly, I am able to get a close clearance without increasing the cost of the assembly. Now let us see how to group the holes, how to group the shafts. As I already told, the TH stands for tolerance of the hole. So here, okay, from here to here is the tolerance of the hole. So this is how much in our problem, it is 0.054. TH is equal to 0.054. Similarly, the TS, tolerance of the shaft, is also 0.054. If you see the value subtracted from 99.928 and 99.874, the TS is found to be 0.054. So from here to here 0.054, the tolerance of the hole 0.054. The tolerance of the shaft is also 0.054. TS is also 0.054 for this problem. Now I have to group the holes. Similarly, I have to group the shafts. So which means that I need to find out F1, F2, F3, F4 value. These are the group limits for the holes. Similarly, I need to find out M1, M2, M3, M4 values for the shaft. These are the group limits for the shafts. Let us see how to find these group limits for the holes and shafts. First, let us see how to group the holes. F1 is the basic size. Okay, B. So the basic size of the hole is 100. So F1 is 100. F2 is B plus K. So what is K here? Now my requirement is I want to achieve a clearance of 0.126 plus or minus 0.2. So 0.2 is the K value in this problem. So B plus K, 100 plus 0.02 is 100.02. So the F2 limit is 100.02. F3 is B plus 2K, which comes to 100.04. F4 limit B plus 3K, it comes to 100.06. But the problem is we cannot have a hole of size 100.06 because all the hole are to be manufactured between the limits of 100 and 100.054. You cannot have any hole beyond the size of 100.054. So as per the formula, it comes to 100.06, but okay, we cannot have any hole beyond 100.054. I am truncating this to 100.054. So I don't have to further see the limits because this itself is covering the upper limit of 100.054. So this is the way in which you have to group the holes. Grouping of the shafts. So we need to find out for the shaft M1, M2, M3, M4, M5, like that. You have to find the limits of shafts, shaft group. M1 is given by F1 minus C bar. So F1 is nothing but the first group, lower limit of first group of hole is nothing but basic size of the hole. So it is nothing but B minus C bar. What is C bar? C bar is the mean value of clearance what you want to achieve. You want to achieve a clearance of 0.126 plus or minus 0.02. So the C bar value is 0.126. So from here the B minus C bar comes to 100 minus 0.126. It is equal to 99.874. So the M1 value is 99.874. Let me write. So the M1 value is found to be 99.874. M2 is B minus C bar plus K. So this comes to 99.894. M3 B minus C bar plus 2K. This value comes to 99.914. M4 B minus C bar plus 3K. This value comes to 99.934. But if you look at the upper limit of the shaft. The shafts are manufactured to 100E8, which have upper limit of minus 0.07 to minus 0.126. So the shaft should be manufactured to a size ranging from 99.874 99.928. You cannot have any shaft manufactured bigger than 99.928. In that case, you cannot have a size beyond 99.928. So we have to truncate this. So the M4 is equal to 99.928. So we don't have to see the further limits because this itself is covering the upper limit of the shaft. So this is how we have to group the shafts. After finding the group limits of holes and shafts, I have written F1 is 100, F2 is 100.02, F3 is 100.04, F4 is 100.054. So these are the group limits of holes. Similarly, the group limits of shafts are found to be 19.874, 19.894, 19.914, 19.928. So we have grouped the holes and shafts into 3 group of hole and 3 group of shaft. Once the holes and shafts are grouped according to the sizes, then we can randomly pick up any one hole from the first group, assemble with any one shaft from the group A. If you assemble this way, you can able to achieve the required clearance of 0.126 plus summation R2. Similarly, second group of hole can be assembled with B group of shaft. Third group of hole can be assembled with C group of shaft. So doing this way, we will achieve the required clearance without increasing the cost of the assembly. We will prove it. So let us say on assembling first group of hole with the A group of shaft, what the clearance we are getting, we will check it. So group 1 of hole assembling with group A of shaft. So what is maximum clearance I will get? So I want to find out the maximum clearance. So take the biggest hole of the group 1, 100.02, assemble with smallest size of the shaft, 19.874. So 100.02 minus 19.874, I am getting a maximum clearance of 0.146. What is the minimum clearance I will get? When you assemble first group of hole with the group A of shaft, what is minimum clearance I will get? Take the smallest hole, assemble with the biggest shaft. So the smallest hole is 100, biggest shaft is 19.894. So the minimum clearance is 100 minus 19.894, you are getting 0.106. So from this, the mean clearance is found out. The adding these two, 0.146 plus 0.106 divided by 2, you are getting the mean clearance of 0.126. So the requirement is achieved. So the requirement is 0.126. Whether K is achieved or not, we have to check. So from the mean clearance of 0.126, how much is the upper clearance is varying? So from the 0.126, the 0.146 is varying by plus 0.02. Similarly, from the mean clearance of 0.126, the lower clearance 0.106 varying by minus 0.02. So on assembling any hole from the group 1 with any one hole, any one shaft from the group A, the clearance is found to be anywhere between 0.106 to 0.146. How you got 0.126 plus or minus 0.2. So 0.126 minus 0.2 is 0.106. 0.126 plus 0.2 is 0.146. So the required clearance is met by grouping the holes and grouping the shafts. Similarly, you can try with the second group of hole with the second group of shaft. You will achieve the required clearance of 0.126 plus or minus 0.2. Similarly, you can try with the third group of hole and third group of shaft. So this is the principle of selective assembly used for meeting the required clearance without increasing the cost of the assembly. Now already we have discussed about the notations. TH is the tolerance of the hole, TS is the tolerance of the shaft, GH is the group tolerance of the hole, GS is the group tolerance of the shaft. So for this problem, what is the value of TH? So TH is 0.054. What is the value of TS? TS is the difference between 99.928 99.874. So TS is also 0.054. What is the value of GS? GH is 0.02. GS is also 0.02. So this problem coming under first type. So for this problem, TH value is 0.054. TS value is also 0.054. So under the first type of selective assembly, TH value will be equal to TS. Similarly, the GH value for this problem is 0.02. GS value is also 0.02. So both are same. So for the first type of assembly, these are the characteristics. TH is equal to TS, GH is equal to GS.